Hey, yo, what's up, guys? Baby Bear 4812 coming at you one more time. And today you guys are getting two problems for the price of one. You're getting problems 1123, which is the lowest common ancestor of deepest leaves problem, and it's actually identical to problem 865. I'm not sure why they do this, which is called smallest subtree with all the deepest nodes. So they work. The code's going to be like verbatim identical, apart from the name of this main method. So tomato, potato, pick your poison. I'm going to run with this one for no particular reason other than the fact that I like the name here, lowest common ancestor, a bit more than like smallest subtree with all deepest nodes. I think it's a bit more intuitive. I think that's just me. If you disagree, well, you can follow along either way. It really makes no difference. So we're given the root of a binary tree, okay, not necessarily a BST, but a binary tree, and we need to return the lowest common ancestor of its deepest leaves. So they give us a definition, a few definitions here. They tell us that a leaf is a node with no children. I think we know that by now. So 6 is a leaf, 7, 4, 0, and 8 are all leaves. The depth of the root of the tree is 0. If the depth of a node is d, then its children's depths are d plus 1. So if this depth is 0, these are 1, these are 2, 7 and 4 are depth 3. The lowest common ancestor of a set S of nodes is the node A with the largest depth, so as far down as possible, such that every node in S is in the subtree of root A. Is in the subtree with root A, excuse me. So if we look at this image over here, we see that the deepest leaves are right here. They're 7 and 4. And we're interested in finding the deepest node that contains both of these. So the lowest ancestor that's got both of them. Technically speaking, 3 is always going to be an answer. So the root of the tree will always be an answer because it is an ancestor to all the deepest leaves. This is true. But we could do better. You could argue that 5 is an ancestor because it houses all the deepest leaves, which is true. But again, we can do better. 2, on the other hand, is as far down as you can go before actually hitting the leaves and saying, okay, I contain all of the deepest leaves within my subtree. And so that's how we would return 2 here. So the question becomes, how the hell do we actually figure this out? Well, that's why we're here. Couple things we want to take care of. So I think there may be a few ways to solve this. The one that I did, which for me was kind of the most intuitive, it's like we got to think of doing a couple things here. One is we actually need to find what the depths are of these nodes. Once we find the depths, then we can go ahead and say, okay, we can identify which ones are the deepest, and then kind of for the second part of the question, actually find which, sorry, my brain's fried today. We can actually find which ancestor is the lowest one, right? So it's also breaking it down into 2 parts. The first part is a bit more trivial. So the first time I did this, I kind of did this, I'll move this over, a bit of a naive way. And what I said was, let me just create a dictionary, and for every single one of these nodes, I'm going to record the depths. And I'm not really sure why I did this, because after I did that, I had to walk through every single item and identify the ones that have the greatest depth. And so, looking back on it now, I think a much smarter way to do this would be to say, let's just do one traversal through this tree. And what we'll do is we'll keep track of the depth at every step. And once every time we hit a leaf node, then we're going to go ahead and say, okay, if I hit a leaf node, then I want to keep track of this depth. And if it's the deepest one so far, we'll just override a global variable called, max depth. And once we do that, what that'll allow us to do is on our second traversal through, and we'll talk about how we're going to solve the second part of this problem, but on our second traversal through, I can just keep track of the depth as I'm walking down and say, if my depth is equal to my max depth, then I know I'm at one of the deepest nodes. I don't actually need to store use up extra memory to store the rest of these nodes. And so what that would look like super roughly, but the code's going to be simple here, this part's kind of trivial, is we'd say, okay, the depth here is 0, the depth here is 1. I'll do like a pre-order traversal, or post order, I guess. In depth here is 0, 1, 2. Okay, so I hit we'll call this the terminal condition. I hit a null node where my depth would have been 3. So I'm going to say, okay, my depth of this leaf here, was 2, right? 0, 1, 2. If my depth here was 2, I'm going to compare 2 to my max depth. So let's say max depth by default was 0. We'll say, okay, cool, this deepest I found so far is 2. I take a step back up, I drop down here, Take a look at 7, go down. Okay, this depth here would have been 4, but we hit terminal condition, so I'll return 3, and I'll say, okay, well, the max depth I found so far is 3. And if we kind of keep walking through here, we go back here, go up the other side and down, we're never going to beat this max depth. And so through this one really simple just depth first search walkthrough, we can identify what the maximum depth is of this tree. Fine. So what we'll do, actually, no, maybe I don't need to necessarily delete that. We'll say max depth is equal to 3. We'll keep track of this. So first part of the problem is just say real easy walkthrough, get the max depth, fine. Now, where this comes into play is in the second walkthrough here. I'm going to start doing a depth first search now. And in this second part, I want to do my depth first search in such a way where if I hit a terminal condition, so sorry, if I hit a null node, I'm just going to return and say, okay, there's nothing I can do here. On the other hand, though, if I'm walking through and I'm keeping track of depth as I go, if I'm walking through and I'm hitting a depth that's equal to my maximum depth, so I'm kind of walking through here, I'm going down this way, I hit this null condition here, and I say, okay, well, nothing I can do there, just return none, fine. So we take a step back, and we go down here, and now, what I'm going to be doing is I'm saying, okay, wait, like, I've found, like, I've hit a depth of 3 here, and 3 was my max depth, because I have access to this variable, and I'm saying, okay, cool, like, so what I need to do something with this variable now. And so what's the key part in understanding this problem is what to actually do with the fact that now we've hit one of our deepest nodes. What we're going to do is the following. Every time I'm making a call, I'm going to store some sort of variable. So I'm going to call these variables left and right. And for each of these, what we're going to do is we're actually going to make a call on a recursive call on the function. So I'm sitting right here. Eventually, I get to this node here 2. Okay. Once I get to this node 2, I'm going to say that left is equal to, let's call the function dfs for a recursive function, dfs of root.left, and right is going to equal dfs root.left, dfs root.right. That's what I'm going to make these variables equal to. Once I get to these variables and I say, oh damn, this depth is at my maximum depth, I'm going to return that variable itself. Okay, so I'm actually going to return a node here, and I'll just denote it this way with a 7. And on my right hand side, because I've realized I've gone to the max depth, these are the nodes that I'm interested in, and I'm going to return both of these. The reason I'm going to return both of these is as follows: is we're going to have a couple of conditions now. We're going to say, let me see where I can kind of fit this in. I really wish I could make these smaller. Like, I'll put it here for now. That's not weird. What I'm going to do is the following: is I'm going to say, where was I? I've got the 7 and the 4. So I'm going to say if left and right. So if I found both a left and a right node, meaning if I found nodes on the left, which are the deepest leaves, and on the right, then I'm actually going to return the root node. So in this case, this root node would be 2. What that's going to do, so imagine I'm almost passing the 7 node up this way, and I'm passing this node 4 up this way, saying, yes, okay, I've found these. 2 has got both a left and a right, and so I'm going to return the 2 up this way. So I'm going to take this root 2, and I'm going to say, like, both of my sides actually contain some of the deepest leaves. However, from this left side here, so imagine we've done our recursive calls, and first we traverse this side, and we hit a null root. We never hit our max depth, so we're returning none up this way, right? So now we're kind of climbing back up the call stack, or I guess rather back down the call stack, and we're sitting at this 5, and what 5 has received is it's received a 2. So this 2 says I'm a subtree that contains the deepest leaves, or it contains at least some of the deepest leaves. However, from the left side, it's getting, I got nothing for you. That means that 5 is not the answer, because 5 is not the lowest common ancestor. Clearly, there's a lower common ancestor coming from here, right? That lower common ancestor is 2. And so, if since 5 is not receiving kind of leaves from both sides, it means it can't be the answer. It could be receiving from either the left or the right side, though. So in this case, obviously, we see it's from its right side where it's receiving these nodes. And what we can do is we can say, so we don't necessarily have a left and right here. If we do have a left, then we're going to return the left. If we have a right, then we're going to return right. And I'll walk up the call stack, and we'll see why we're doing this. And finally, otherwise, if we have neither of these, we're going to return none, which is capital N for none. And so following these conditions, why is this going to work out kindly for us? Well, let's think about what we're returning here. We're returning a 2 up here. So 5 has received, a none from this side and a 2 from here. Since it's received one of the sides, it's not gonna push itself up because it doesn't have deep sleeves coming from both sides. It's just going to push along the right side that it received, and it'll go up this way. So the 3, our root node now, is only going to be getting the lowest common ancestor from that one side. After we do our traversal here, notice here that we never hit any of our deepest sleeves, so we're going to be returning none here. 1 is going to receive nothing. So to quote Shakespeare, nothing comes from nothing, and we push nothing back up this way. And once we get to the bottom of the call stack on our initial call, this root node 3 will have noticed that on its left side it received 2 as the lowest common ancestor. On the right side it received nothing. So it must be then, by the conditions we wrote out here, that it's going to return the left if it's got the left, right? Noting that it didn't have both from the left and the right side. If we were to entertain an example where, let's say, maybe I had a 5 right here, or actually, so I think they tell us the nodes are going to be unique. So not that it matters here, or the node values are going to be unique. Let's say I had a 9. In this case, we would actually return a 9 upwards. And what would happen was we push this 9 up here. This node 1 would receive orders from one side that it does have in like a lowest common ancestor. It would push that 9 up here, and now all of a sudden 3 is receiving both a 2 and a 9. So it's saying, damn, like I am an ancestor of 2 lower ancestors, both of which have lowest common leaves. And so in that case, our result would be 3, because the lowest ancestor to these 3 actually happens to be the root. This is, I've modified this example, so I'm going to undo this now. And so in this case, this is why through this through this traversal, this is how we would only return the 2. I hope that explanation made sense. If it didn't, again, and I say this every time, I think the code will help a bit in the understanding. Let me know in the comments down below if you've got any questions so far. Otherwise, let's dive into the code. So we're going to tackle 2 parts. We're going to find the maximum depth, and then we're going to go through with actually grabbing the lowest common ancestor. So why don't we do this? Let's make a bit more space here. Let's move my big head back down, and I'll do the following. Okay, so we want to say the following. So we want to get max depth, and then we want to get, I'll call it LCA for lowest common ancestor. What I'm going to do is I'm going to define a function called get max depth, and maybe actually, why don't I do this? I'll say get LCA, and that's going to be some function. And this is going to be some function. I can delete these comments because we have these as placeholders. All right, so what am I going to do here? I want to have some sort of max depth that I'm going to have access to later. I'm going to initialize it at 0. And then what I'll do is I'll call get max depth. And what we're going to have to do here is pass in the root and some sort of current tracker for current depth. So we'll call this root, we'll call this depth. Since we're going to be modifying maximum depth, again, for those of you who've been watching me long enough, I always like to do it. So I'll declare non-local max depth, and then that way we can modify it. And what we'll say is this. We'll say if we ever hit a null node, so if not root, we're going to want to set max depth to the maximum of whatever value it's at itself, or I'm going to say depth minus 1 here. And the reason I'm saying depth minus 1 is imagine we're walking down here. So this depth is 0, depth is 1, depth is 2. I get down here, depth is 3, but I've hit my terminal condition, so I'm at a null node. So that means that my previous item would have been kind of the last real depth that I had. So that's why I'm going to compare it to depth minus 1. If we haven't hit this condition though, then that means that we still have trees lower down. So I can call get max. Sorry, not trees. I've got potential child. I don't even know if I have child nodes. All I know is that I'm a node, and I'm going to keep searching downwards to see if I can get any deeper. That's what I meant to say. Get max depth of root.left and depth plus 1. And then we're going to do the same thing for the right side and we're going to pass that downwards. And there's nothing else that we're going to need to return here. I'm just making sure that I'm not being headless here and forgetting something. But that should be it. We'll give this a run after, and we'll see if it works. But that should be it in terms of just grabbing the actual maximum depth. Now, let's do the following. So we're going to have this get lowest common ancestor, and we're going to have to pass in the same things. We're going to have to pass in a root and a depth, and that depth will help us keep track of how far down we are, so we can say if my depth ever hits maximum depth, then kind of call it quits, or not call it quits, but identify, okay, this is one of the deepest nodes that I've got, and so we need to see if we're going to push it upwards, right? And this one's actually going to return an item itself, so I'm just going to return get LCA, and we're going to pass in root and depth. So starting depth is 0. I think we are told in the conditions, by the way, that so there's going to be at least one node, no matter what. I should have mentioned that earlier, but I did check it before answering the question, and it tells us again the values of the nodes in the tree they're unique. Doesn't really change anything for us here because we're not comparing values. We're actually referencing the nodes in memory as they are. So let's hit our terminal condition. We said was if not root, then we're just going to return none. There's nothing we can do here. Otherwise, if depth is equal to maximum depth, then we're going to want to return the root node itself. If I hit down to the 7, I say, oh damn, that's as deep as I can go, like I've previously recorded my max depth. Cool, push this back upwards so we can notify our parent that I'm one of the deepest nodes. Okay. Now, if we're not if we're not at our maximum depth, so let's pretend that we're right here, we're sitting at this 2. If I'm sitting at this 2, and I notice that if let me do this. Sorry. Even before I do that, I kind of mentioned up here we'd be calling a left and right just to identify. So to make our calls to either child, I'd say that left is going to equal get LCA of root.left depth +1. So we're going down 1 level. And right is going to equal get LCA of root.right and depth +1 as well. Now, if left and right, meaning if I'm at my root and I notice that, okay, like I've got left child and right child, or like both of them contain these deepest leaves, then that's wicked. That means that I'm an ancestor and I need to push myself up. Okay. If I have one of these but not the other, so if I have one of these but not the other, so I'm the 5 now, and I say, okay, well, I'm getting nothing from this left side, but I'm getting something from the right, then I want to return the right side. Excuse me. So we can kind of make this a long drawn statement. So we can say something like if left, return left, if right, return right, else return none. So we've got nothing. Instead of doing this, just to make it a bit more succinct, what I'm going to do is I'm going to say return left if we actually have a left side. Otherwise, return right. And if right is none, so if we don't have a left, it's none, and right is also none, then by default we're going to return none. And that should be it in terms of the code. So again, this is just saying if I have if I have any root that's been passed up from the left side, pass it along. So keep pushing it up. Almost like in this case, 5 almost acts as a carrier, and it says, well, I'm not a lowest common ancestor, but I know somebody who is one of the lowest, potentially one of the lowest common ancestors. So I'm just gonna do my due diligence. I'm gonna be good to society, and I'm gonna help promote him and push him up and say, hey, like I found one, and we're gonna push it up to the 3, and I found one. If eventually we get to the 3, and 3 hears from its left side, hey, I found one, but it hears jack all from the right side, then it says, all right, cool, we're running with the one we found, and that's this 2. Again, if we had a 9 here, and maybe there was an 8 that was then passed along through here, it said, whoa, I hear noise coming up from both sides. It's my job to take care of this now. Then we return the 3 along. And so let me run this super quick. None has no attribute left. Previous line repeated one more time. So this is happening where? Line 8. What did I do here? Oh, whoops. So what I forgot to do was after in this condition here, if not root, we actually need to return because we don't want to keep running through the rest of the code, do we? That would be pretty senseless. So as you can see, I've ran this a bunch, and there we go. So let me close this up. I'm not aware of whether there's a way to do this all in one pass. I highly suspect that there is not, because I'm not really sure how we would. I don't think there's a way for us to identify whether or not we've hit the maximum depth without at least once having gone through the entire tree to acknowledge what that maximum depth is. Like, imagine, we tried answering this question we got here, but then this, this side had like a whole bunch more, and then what do we do with all the rest of this stuff, which we've already kind of done? So I think that we need to do two passes. Albeit, even though we're doing two passes, it's still linear in time. So getting the max depth is linear in time. Getting the lowest common ancestor is linear in time as well, because we're tapping every element only once. Space-wise, we would have it. So space-wise, the only space we're really taking up would be the size of the recursive stack. And so that tells me that if it's the size of the recursive stack, then it would be, at worst, it would also be O of n space, where if we had the entire height of the tree, so the maximum call stack size we'd ever have would be the height of the tree. If our tree was just kind of like one linked list going straight down, then in that case we'd fill up the call stack with n elements. So all that to say, O of n time, O of n space, we tackle this by first finding the maximum depth, and then working our magic here to actually identify, if I get down to kind of a leaf node and one of the deepest leaf nodes, then I'm going to say, okay, cool, like I'm a leaf node, I'm going to push myself up, and then we need to identify whether or not it's the lowest ancestor or not here, kind of in this section. Hope you guys enjoy that. Again, this is problem 1123, which is the same as problem 865. Like, comment, share, subscribe, all that fun stuff, and thank you guys for watching. I'll see you in the next video. Peace.